So this is the question 2 for homework, the end of probability, and this the second question is first part is I'm gonna explain what a Markov chain or Markov process is. So according to our notes, we can see that what a Markov process is, that we can clearly see the definition that xt is a Markov process if the past has no influence on the statistics of the future on the condition the present is known. So it's basically saying that if we have the current input, that if the present is known, then the past, that is the previous outputs, will have no effect on the outputs that are yet to come. And we also get to know that Markov process is determined if we know the second order distribution, that is if we have x1, x2, t1, t2 in the first order statistical distribution functions where f x1, t1, second order is just x1, x2, t1, t2. Also, we now get to I'll be explaining also stuff like stationary processes, in which we have basically two kinds of processes that are wide sense stationary and strict sense stationary. So we see that so basically what it is that a process is called stationary if we see that there is no change across the ensemble of the process. So if we see that a process is going on right now, and if we see that a process is say after a certain time period, if we say that the process is still going on then, so if you see the variables of the process, they're going to be the same. It's going to be stationary across time. So if it is going to be stationary, that's if it's going to be same across each and every time instant across the entire ensemble, is across ever time since the beginning of time till the end of time, if you see all those time samples, and if they all turn out to be identical, then it's called a strict sense stationary, that it is stationary throughout, that is at every time interval. But that's hard to do because we actually cannot physically prove that it's going to be same at all the time intervals, because they're infinite time intervals. So what we get is a more toned down version of that toned down definition, which is called wide sense stationary process. So this wide sense stationary process actually incorporates all those definitions of a strict sense stationary process, but it's not that specific, not that categorical. So now I'm going to tell you three definitions of a wide sense stationary process, which actually imply to the strict sense stationary process also. For a process to qualify as a wide sense stationary process, the first condition is that the mean, that's the xt, this or eta t, that's the expected value, should be constant. It should not be in terms of t. It should not have any variable, if it just be a constant value. And secondly is that the autocorrelation function t1, t2 should just be a function of tau. That is actually the difference. Tau is the difference between t1 and t2. That's the time difference. So the autocorrelation function should be a function of tau. That's the time difference. These information, that these 2 points are sufficient for a process to be a wide sense stationary process. However, it is not enough for the process to be a strict sense stationary process, in which case we then have further conditions which the process has to qualify in order to be that. The next process that I'm going to talk about is the normal process. So we actually see that a normal process is also known as a Gaussian process, which is the same as what we learned earlier. That is a normal variable and a Gaussian variable are the same, a random variable. So the process xt is said to be normal or Gaussian if the random variables, all the random variables within this process, if they're jointly normal for any n. So basically what we get to know is that all the random variables that are inside this have to be jointly normal. For this, we actually have a couple of conditions which are to be satisfied. Which means that for all the variables, so we see this is the nth order statistics, that's from x1 till xn, and then from t1 till tn, we have 1 upon root 2 pi to the power n root of determinant c e to the power minus 1 by 2 x minus e times the transpose, and then c inverse of that x minus eta. So what this is basically that, and we also know the statistics of a normal process, they have to be determined in terms of the mean, an autocorrelation function, and autocovariance, that's c. So c we see up ahead as the autocovariance function. And also we then now further have an example in which we've been given a process and we're given its expected values, and we were asked to find out a couple of stuff when we know that it is a random variable or not. The next topic I'm going to talk about is white noise. So what white noise is, basically that, first of all, why do we call this noise signal white noise? It's called white noise because it basically has all the frequencies, just like white light has all the frequencies of light, and it's a mixture of all the lights. White noise has all different frequencies, and it is a mixture of all the various noises. So we're told that the definition, the theoretical definition of white noise, is that it is a zero mean that's always assumed white noise, and that its autocorrelation function is qt into del of t1 minus t2. And in this, we're told that the qt is called the average intensity. Then further ahead, we are given an example in which we're told about the white noise, and we're further supposed to enhance on it. So we also get to know that when a system has an input of white noise, what the response is usually. So we have a theorem regarding to that, which says that the input to a linear system is white noise. If the input, that's what we've entered xt, if that is white noise, then the expected value squared, that's EYT, that's the output squared, is going to be, that's also known as the average value, average power, sorry, is the value of qt convolved with xt squared. So that's actually the impulse response of the system once we get to know of it, which can also be written as, because it's a convolution, so minus infinity to infinity q of t minus alpha h alpha squared e alpha.